autonomous mobile robot. We'll just call it AMR for short. Okay. The features when we talk about autonomous mobile robots, what should come to our mind will be, it's a robot, of course, it's mobile, and the keyword is autonomous. Autonomous means it's able to move on its own without human intervention. So that's the keyword, without human intervention. And how that comes about, how we do that, and so on. So we'll go into some details of that in a while.
Students need to develop something from scratch. As one example is here. This one is a year one project. Let's say some of our students are here. You can ask them later. You can see some similar this kind of robots in the booth in there. This is the year one project. Year one project, let's say next student based on this platform, they continue to develop. Let's say they have something like this. This is the year two project. So in this kind of project, what are the learning outcomes? What kind of things that our students can learn? Let's say here, let's say there, inside for this kind of autonomous mobile robot, there are 4 important subsystems. Here, mechanical part, right? We understand that without a mechanical part, we cannot call this one as a robot, or you only can call it the chat robot, right? For the real robot, we know we need a mechanical part. Then after that, we need the electric part to drive it. Mechanical part itself, it cannot move itself, right? We need some power to drive it, right? Electric is one of the power sources. Let's say you can use wind or some tide or some other power sources to drive it. But here, let's say especially for an indoor application, we use the electric part to drive it. Then for the electric part, let's say it's not enough because since we call it a robot and we call it autonomous, why it is autonomous? It means without human intervention, right? It can sense the environment and can make a decision by itself. How to achieve that? We need various sensors. So here, we need to introduce the electronics part. Then, the real important thing there, let's say we need a software to integrate them together and to analysis, to make decision. And here, that's why we have a software part. Somehow, let's say here we call firmware. It means it's a kind of very low-level software to drive this kind of real-time tasks. Yeah.
Some of you will be curious, what do you go through if you go into this program? So this will be a brief overall. What are the modules you'll be taking on if you come into this? So this Mechatronics program is a 4-year program, right? So within the 4 years, these are all the modules that you would have to go through. Starting on the left, these are the first-year modules. So you'll see that these are probably something you are quite familiar with in terms of subject names, because these are the foundational modules, right? You need to build up your foundations before you move on to engineering-specific modules. So you can see briefly, yes, the one on the leftmost, that will be your first-year modules. Then you're moving on to the second-year modules, where you go more into the details about programming, digital design, mechanical design, embedded control designs, and so on, right? So with that, then you'll be able to move on or work in parallel on projects. So if you look into here, over here, these are the project modules. So you can see that the emphasis is quite heavy on project modules. For example, if you look at the system project modules 1, 2, 3, capstone 1, 2, and so on. The one that we showed earlier, the robots, autonomous robots and so on, that is part of these 3 modules, project modules. So I think Dr. Tang will talk more about this.
Yes. So here, let's say this platform you can see actually is from this course, System Engineering Project 1, which is in the year 1. Actually, these are just a listed project. We call the project modules. These modules are just do the project. But in some other classes, for example, the one course called the Computer Environment, there, students also have a kind of side project. And in the robotics, students also have a side project. They need to do something over there. So you can see this program is quite project-oriented. why we design this. So here, let's say I share, let's say DigiPen, this one program is a joint program between DigiPen and SIT. DigiPen is from American, is from American Seattle area. So DigiPen has quite a lot of this kind of industry experience. Let's say we know, let's say what are the best way to learn. So learning by doing, right? You do something. And by doing a project, you can apply what you have learned. For example, for this one, you learned some physics. Let's say how to drive this one, what is speed, what is the acceleration, let's say you need analysis, this kind of thing, right? So this is the physics part. We can apply this kind of stuff we learned from the physics part here. And something is for the mathematics, let's say inside, let's say maybe, let's say I have learned the integral. And then here, let's say we need to apply the integral here. And mathematics, let's say from the linear algebra, I learned the matrix, the operations. I also applied them here. So the project is the platform. Let us to integrate, to apply what we have learned, then integrate them together.
Right here, which is what we call IWSP, which is short for Integrated Work Study Program. So this is where all our students, every one of them, will be attached to a company. So that's where they gain industry experience. Okay, and during that period, we encourage the company to treat all our students as if they are their engineers, employees, and so on. So they work and they experience the real work life, how engineers work in the companies out there, right? Anything to add on this? Yeah, so this part, a very important part of the program. So that's where all students will be there for the whole of their third year. And when they are back in the final year, that's where they work on their capstone projects. So these are the two that will span over the whole of their final year, in addition to some other modules, for example, control modules from robotics and so on. These two are the final year modules.
So here, let's say what you can see, this demo, let's say, is on the remote control. When the students go to the project course 2, let's say, still based on this mechanical power platform, but they need to start to let it to be kind of autonomous. Let's say autonomous, let's say we see the very simple thing. Let's say, would you please, let's say turn 90 degree, let's say somehow let's say turn 90 degree. Let's say turn, this turning. For this one, under the remote control, let's say you just press button, let's say you can visually see. Right now, let's say I need to change the angle, right? Change the heading. Already changed it. Do I reach the target or not? Let's say originally is, let's say, for example, is 90 degree, I need to change it to 0. Once I reach 0 degree, I stop, right? This is under remote control, very easy. But how does it to stop in an autonomous way, right? So in autonomous vehicle, let's say I give our instruction, let's say move to over there. Somehow I know the path, I need to turn, let's turn 90 degree, right? Even this is a very simple, very basic requirement for an autonomous vehicle, right, to turn. How do you know, let's say, the turning angle is correct, right? So to turn, actually, for this kind of vehicle is easy. I just differentiate the two-wheel speed. One speed faster, one speed slower, so I can turn, right? I just tilt like this. But the important thing is that, let's say, for example, let's say right now is 90 degree. I need to turn to 0 degree. I need to turn to here. I need to know, let's say, whether I already reached this 0 degree or not. To achieve that, inside we need some sensors and analysis. So, for example, for this one, let's say one example is that we need the so-called the IMU sensor, which includes the accelerometer and the gyroscope, this kind of sensor, to sense what? Linear acceleration and angular speed. By analyzing this and some signal processing, then we can know what is my current heading. Let's say the current heading is 90 degree. Let's say I need to turn to 0 degree. So I keep calculating. So I know right now what is my heading. If I know my heading is 0 degree, I stop. I know, let's say, the turning is done. Then I keep moving, right? You can see, even for this very simple, let's say, looks like a very simple behavior, but underneath, there are quite a lot of stuff, right? If you want to let it to be autonomous, right? Because it makes decision by itself. Let's say, of course, the human, let's say, we need to give certain instruction, let's say, in a high level, this one, let's say, move to over there or something, or detect what kind of thing I need to give this. Then after that, it makes decision by itself, right? To do that, so we need to quite a lot of analysis and sense the environment.